There is one final method that we can use. It is actually very direct, and it's something that you would have already practiced a bit, because one of the first things that you do when you learn about logarithms is how to translate an exponential statement into a logarithmic statement. Well, this is exactly the type of statement that we would have had to do that. So, as long as we are in the prescribed form, we can simply rewrite this into its equivalent logarithmic form. That is to say, the logarithm base 5 of 18 equals x. Actually, that probably requires the least writing of all of them. That does not necessarily make it the best option. Now, like the first option where we used the logarithm base 5 on both sides of the equation, we now would need to use the change of base formula, again with either common log or natural log. So we do still need the change of base formula if we do it this way. If we're fortunate enough that the original function is already base 10 or base e, then actually that saves us a bit of time, but for any other base we would end up in this form and have to use the change of base formula to evaluate it. Simplest, least writing, as long as the exponent expression is simple enough. So now let's take a look at another problem where that exponent expression is not quite so simple, where it's not just the plain variable, but it is instead some other expression. For example, suppose we're looking at 4 to the 3x minus 1 is equal to 1024. So we have, again, our three options here. And what we're going to find is that in a case like this, the first option of using the logarithm base 4 on both sides is probably the cleanest. So what we would do here is, again, the logarithm base 4 of both sides of the equation. Now, yes, this way does require to use the change of base formula at some point over here. But it has the advantage of simply canceling those out and not needing to rearrange things, not needing to rewrite them in new places or move things around. We literally just get to cancel those out, and what we're left with is the expression from the exponent. And that's pretty clean. That's pretty clean. You can't get much better than that, to be honest. Now from here, we use the calculator to evaluate this, and we undo the remaining operations. At this point, this is actually a linear equation because it is x times a variable, or I'm sorry, x times a constant with the addition or subtraction of a constant and a constant. As ugly as it is, this is still just a constant. So we use the change of base formula to evaluate this. And as it turns out, now I chose it this way on purpose, it won't always be this nice, it does actually provide us with a nice value. So as you can see here, this is actually, again, the linear equation that I described before. So we can do the usual things of adding 1 to both sides and dividing both sides by 3. And that gives us x equals 2. So again, this is the purpose here is a little bit less about this and more about why did I choose to do that as opposed to the other two methods. Well, let's take a look at the other two methods. Let's suppose instead of matching the base of the logarithm, I used the second method. Which is to use the natural or the common logarithm. Again, it does not matter which you're using. Now, what makes this different and perhaps a little more difficult is that the expression in the exponent has to be treated as one item. Yes, it has multiple things going on in it, but it has to be treated as one item. So when we use the power property of logarithms to bring it down in front, we have to be very careful to write the 3x minus 1 in parentheses. Now, again, this will, if done correctly, give us the same result that we got before. But here's the tricky part. In my experience, many people will forget to write those parentheses. And if you're honest with yourself, you might admit that you're one of those people who would forget them. And that can lead to a lot of issues. Without the parentheses there, there's no reason to treat this log 4 as affecting the whole statement. Without the parentheses, it might look like it's only affecting the 1. And that will change how you handle the rest of the equation for solving it. It makes a very big difference, those parentheses. So if you do correctly use the parentheses, this will work fine. We would divide both sides by log 4. And at this point, we're in the same position we were with the first method. This is just written in the form of the change of base formula, which again is the idea of using the common or natural log as opposed to matching the base of the exponential. We don't need the change of base formula, it's already built into what we're doing. But that really is a big pitfall. That happens a lot where people forget to write that set of parentheses and it really messes up the whole thing. We actually run into the same basic problem if we try to rewrite this in its equivalent logarithmic form. Not as often, but it does tend to happen. Again, it's got the same pitfall that you have to remember that the entire expression in the exponent has to be treated as one item at this step. We could then, from here, write the equivalent logarithmic statement, the log base 4, and then switch these two. So the 1024 is on the left, and the 3x minus 1 is on the right. Not as bad as the last one, granted, but again, it still kind of has that thing where you need to remember that this is one item and cannot be, you can't deal with the 3 and the x and the minus 1 as separate entities until you've reached this point. So for that reason, I think that matching the base of the logarithm and to the base of the exponential is probably the cleanest, most standard method to use. I would continue to use that, but you use whichever of these three works for you and whichever makes the most sense and helps you get the problem right. They each have their things. You either need the change of base formula or the power property of logarithms, or you need to remember how to translate to equivalent logarithmic statements. But whichever of them you use, they will get you there if done correctly.